Hello.
Hello, sir.
Okay, we'll continue with problems on thermodynamics. This one is, I'll write this down. This is the figure. There is a chimney sort of a structure. So, ideal gas of density rho is equal to 0.2 kg per meter cube enters a chimney of height h, enters a chimney of height h at the rate of alpha is equal to 0.8 kg per second. This rate of entry is at the lower end and escapes through the upper end as shown. The cross-sectional areas are shown A1 and A2. Here A1 value is 0.1 meter square and A2 is 0.4 meter square. The pressure and temperature of the gas, pressure and temperature at the lower end are 600 Pascal and 300 Kelvin. The temperature at upper end is 150 Kelvin. Chimney is heat insulated, is heat insulated so that the gas undergoes an adiabatic expansion. Adiabatic expansion. Take the value of G to be 10 and the gamma for the gas to be 2. Ignore atmospheric pressure. Ignore atmospheric pressure. Which of the following statements are correct? First is pressure at upper end is 300 Pascal. Second is velocity of the gas, velocity at lower end is 40 meter per second and velocity at upper end is 20 meter per second. Third one is height of the chimney. Height of chimney is 590 meters. And fourth one is density of gas. Density of gas at upper end is 0.05 kg per meter square. So we have to select which statement is correct.
Okay.
They have asked you to ignore atmospheric pressure. So this seems like a fluid flow plus thermodynamics question, right?
Right.
So try it out. Easiest thing to calculate is the pressure at the upper end,
Uh,
because they have told you that it is adiabatic
Adiabatic
expansion,
expansion.
and they have given you pressure and temperature at the lower part and temperature at the upper part.
Yes, sir. Pressure at upper end is not 600. It's not 300 Pascal. It's 150. So
Hmm.
that's
This is wrong.
yes, sir.
Pressure at the upper end is 150.
Hmm.
Now you can even find density and all at upper end,
Hmm.
because you can use ideal gas law to get density.
Yes, sir.
They had given you density at the lower end, by the way.
Yes, sir. Sir, is it multi-correct or single correct?
Multi-correct could be there.
Okay.
Focus on the density part first.
Yes, sir. Yeah. So, by T.
The ideal gas law can be converted to get density.
Yes, density is PM by RT.
So P capital M by RT, where capital M is molar mass,
Hmm.
right?
Yes, sir.
So density at the lower point was given, and you knew temperature and pressure of lower point, right?
Yes, sir.
Capital M and R will remain constants. So you will just need to compare row 1 to row 2, right? At the upper end.
Yeah. So pressure was 600. So at upper end, it's not 0.05, it's 0.1.
Right. So it is also wrong, right?
Yes, sir. Uh,
Okay. So two of the options are wrong. Now let's think about the velocities,
yes, sir.
because you know density and you know rate of mass at
Mass
which it
flow.
was entering, right?
Yes, sir. Mass flow rate.
And you know now density of the upper end also, actually.
Yes, sir.
If you divide the mass rate by the density, you would get the volume rate.
Mass rate by density. Yeah, like
Like mass by density is what? Volume.
volume.
So
You
if you
would get the
divide that, you'll get
what?
the volume rate at which gas was entering.
Yes, sir.
That would be the A1 V1 type of term, right?
Yes, sir.
So that is what you should do.
Sir, option 2 is correct.
Hmm. So you are getting 8 is equal to A. This mass rate divided by the area here is going to give us the volume rate, right?
Yes, sir.
So that is going to be 8, I think.
Hmm.
8 is equal to A1 V1, right?
A1.
And A1 is 0.1.
Hmm.
So you'll get 80 is equal to V1, something like that, right? But why are you getting 40 then?
No, 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 no.
1 second.
Mass by
Ideal gas of density this enters. The density is 0.2 at the bottom.
yes, sir. So,
Okay, so we are dividing it by zero point 0.2, not zero point 0.1.
hmm.
So 0.8 by zero point 0.2 is the total volume rate, right?
Yes, sir.
Now it's fine because it's 4.
Yeah, 4.
4 is equal to 0.1 into V1,
Hmm.
right?
Hmm.
So that gives V1 as 40.
Hmm. And
And
similar.
now you can just compare A1 V1 to A2 V2, right?
Yes, sir.
Because overall has to be same, right?
Huh.
And you can see that the ratio, actually, however, it doesn't have to be same because that was for, remember, you cannot do A1 V1 is equal to A2 V2. Do you understand why?
Because we have different conditions.
Densities.
Yeah, and yeah.
No, not random things, not conditions. Because it's different densities.
Yeah.
Why? When we did this equation, if you remember, it was for an incompressible fluid.
Yes, sir.
Incompressible means what?
It's
Density remains constant. It cannot be compressed.
yes, sir.
But here is density remaining constant.
No.
So here we have to equate conservation of mass we have to do, right?
Hmm.
So we got V2 as 40. We need to find V here, right?
Hmm.
So area into this V will be the volume, but then that volume you should multiply by the density at this location, right?
Yes, sir.
That should be the mass rate at which it flows out, right?
Yes, sir.
That should be equal to zero point 0.8, no?
0.8. Yeah.
So we are doing law of conservation of mass. We cannot do equation of continuity directly.
Hmm.
Do you understand what I'm saying?
Hmm.
If you do just this one directly, you will get the wrong answer.
Hmm.
Is it clear?
Yes, sir.
So this is correct. And then we have to figure out height of the chimney. For that, you have to do work energy theorem. You can try doing Bernoulli's
But
equation also to get that. Remember that densities are changing.
hmm.
Just use Bernoulli's theorem to get the height difference, right?
Yes, sir.
You already know P1, P2, you already know V1, V2, so it should not be very difficult to do Bernoulli's.
Yes, sir.
This option will not match, okay?
Yeah.
It is not 590. It will come something like 360 or something. You should
Yes.
check it out, check the calculations, but it is fairly easy. You just have to apply Bernoulli's principle and you will get it. Or you can do a direct calculation also of work done by all things, and that is change in kinetic energy. So in that case, you will do work done by this pressure P1A1, work done by this pressure P2A2
Okay.
on a portion of the thing delta x1 and here delta x2. Uh, then you will also do work done by the gas adiabatic work done
Right.
and work done by gravity. All of the things should be equal to the change in kinetic energy of the gas. So
Right.
basically, that's almost like doing the derivation of Bernoulli's. In
Yeah.
Bernoulli's theorem, you do a small section of the fluid, right?
Yes, sir.
Work done by one side P1A1 delta x1, then other side P2A2 delta x2.
Yes.
On all of the components you write down to be equal to the change in kinetic energy. You can try that, it will not come. Uh, Check it out later. We'll move on to the next problem. This question has a diagram. Okay. So These are insulators. So he's saying a thermally insulating cylinder has a thermally insulating and frictionless movable partition. Frictionless movable partition in the middle as shown. On each side of partition, there is 1 mole of an ideal gas with a specific heat at constant volume. This ideal gas has CV is equal to 2R. Initially, each side has initially each side has V naught and T naught volume and temperature. Left side has an electric heater. This is an electric heater which is turned on at very low power to transfer heat Q to the gas on the left side. Low power transfers heat Q to the gas on the left side. As a result, partition moves slowly towards the right, reducing the right side volume to V naught by 2. Consequently, the temperatures on the left and right side, the temperatures on left and right side become TL and TR respectively. Ignore the changes in temperature of the cylinder, heater, and partition. Uh, yeah, and then you have to find out first of all the value of TR by T naught, and secondly, you have to find also the value of Q by RT naught. The partition moves slowly.
Hmm.
This was a low power and it has transferring heat Q to the left side
Yes.
heater. Notice that a slightly weird value of CV was given, right?
Yeah.
What does this tell us?
Polytropic process.
But which type of gas is it? What are the degrees of freedom here and so on?
Um, Degrees of freedom here
Because you need to know lambda for the gas, right?
would be right. Mm,
So
uh,
technically, lambda is calculated easily actually. If they have given you CV, CP will be
CV,
CV is 2R. What is CP?
1 second.
Obviously, it is 3R. No, Cp is always Cv plus R.
Right.
By the way, you need to know equipartition theorem. Do you know what that is?
Uh, one, 1 second. The the total energy of the gas uh,
Hmm.
is equipartitioned into in the
All the degrees of freedom contribute equal amounts of energy.
yes sir.
And it is for 1 mole of a gas, it is R by 2, right?
I'm
Number
not
of degrees of freedom decides how many R by 2s are there.
right, right.
So here the degrees of freedom are 4 because it is 2R CV,
Yes sir.
right?
Yeah.
If every degree of freedom there is R by 2. When there are 3 degrees of freedom, it is 3R by 2.
Hmm.
That is for a monoatomic gas, 3 degrees of freedom.
Hmm.
Here it is 4 degrees of freedom. That's why it is 2R, right?
Yes sir.
You need to know this, and if you haven't revised it, you need to revise it from HCV thermodynamic specific heat capacities chapter.
Yes sir.
But lambda can be calculated without knowing that also, because you know Cp is equal to Cv plus R. So C lambda is 3 by 2,
Hmm.
right?
Yes sir.
Now, this part of the gas, obviously it was gaining heat from the heater, right?
Yeah.
But what about this gas?
No, it's not.
So this
Meaning,
gas is completely insulated, so obviously it will be doing an adiabatic process, right?
yeah.
So the process for the second gas is adiabatic, right?
Huh.
So they are asking you for TR by T naught, and we know finally the second gas's volume has become V naught by 2, right? Temperature has become TR, right?
Yeah.
So we can easily do adiabatic compression for this, right?
Yes sir.
Starting point was T naught V naught, now it is V naught by 2 TR.
Hmm.
So we can use that equation TV power gamma minus 1, correct?
Yes sir.
Gamma is 3 by 2, so 3 by 2 minus 1, so 1 by 2 is equal to TR, and now it is V naught by 2 to the power 1 by 2, right?
Yes sir. So
So TR by T naught is simply equal to root 2, right?
yes sir.
So the first part of this question is actually very easy, direct, simple adiabatic you have to realize, right?
Hmm.
All you need to know is gamma value.
Yes sir.
This is one question of a paragraph. Second question now you have to try, which is the ratio of Q by RT naught. You have to be patient and do it in a step-by-step manner. See, if they ask you for Q by RT naught, they want you to do work, first law of thermodynamics on this gas, right?
Yes, sir.
Then only you will get the Q term, right?
Yeah.
So first law of thermodynamics on first gas is Q is equal to work done by gas 1 plus delta U for gas 1, right?
Yes, sir.
You have to basically get both these terms.
Huh.
Okay. Now slowly you have to think of each thing, how to find that. See, direct calculation of work done by gas 1 might be slightly annoying, but you can find out work done by gas 2, right?
Hmm. Um,
Because it is undergoing a compression, it does negative work, right?
right.
Adiabatic compression is happening for it.
Yes, sir.
If you can find out work done by gas 2, work done by gas 1 will be negative of that or positive value.
Right.
Because both the gases are doing work against each other, right?
Yeah.
So let's calculate first work done by gas 2.
Okay.
So for the gas 2, the first law equation is like this. 0 is equal to work done by gas 2 plus delta U2, right?
Right.
So work done by gas 2 is equal to negative delta U2.
Hmm.
So now delta U2 for it. We know the final temperature is root 2 times original temperature, right?
Yeah.
So delta U2 for gas 2 is equal to NCV delta T, right?
Yeah.
N is 1, CV is 2R,
Hmm.
delta T is final temperature minus initial temperature. But we know final temperature is root 2 times initial temperature.
Yeah.
So it will be root 2 minus 1 T naught, right?
Hmm.
Delta U2 is coming as this, right?
Yes, sir.
Minus delta U2 will be work done by gas 2, right?
Right.
So work done by gas 1 is what?
Uh,
Plus.
yeah.
So it will be 2 times root 2 minus 1 RT naught.
Hmm.
So we have found work done by gas 1.
Yes, sir.
Because we calculated work done by gas 2 and it will be opposite of that, right?
Yes, sir.
Okay, fine. Now we need to find this part, internal energy change for part 1. Again, we have to do NCV delta T, but we don't know the temperature of this final part, right?
Hmm. But,
So for that, we have to figure out what to do.
sir, but it's like it's a piston. So I mean, not piston, like the partition. On both sides, it's in equilibrium, right? Because it's
The only thing that will be equal is pressure. There is no heat
pressure.
exchange,
Right. So
right? So pressure you can say will be equal
yeah.
on both sides.
Right.
So you can sort of find the pressure here if you want. right?
Or
See, using PV is equal to nRT, we can see here that pressure is proportional to T by V, right?
yes, sir.
So pressure is proportional to T by V.
Hmm.
So notice that for the second part, temperature has become root 2 T naught
Good to
and
know.
volume has become V naught by 2, right?
Yeah.
So pressure has become root 2 times, 2 root 2 times the original, right?
Yes, sir.
So we know that if the initial pressure was P naught both sides, it is 2 root 2 P naught now, right?
Yes.
Correct?
Yes, sir.
Because it is in equilibrium, you are saying final pressure on the left is also 2 root 2 P naught, right?
Yeah.
Now notice that the volume of this part has become how much of the initial value?
It has been 1 second.
Volume of the left side as a multiple of initial volume. Obviously 3 by 2 V naught, no?
Yes, sir.
Because total volume was 2 V naught and now it is only V naught by 2 here.
Yeah.
So 3 by 2 V naught is the total volume and this is the pressure final. Now again using gas law PV is nRT, we can see that temperature is proportional to the product of PV, right?
Hmm.
Initial it was P naught, V naught, T naught, right? But
Yes, sir.
final temperature final now will be what? 2 root 2
Two.
into 3 by 2 P naught, V naught, right?
Yes, sir.
So it is TL will be 3 root 2 T naught, right?
Hmm.
Do you understand what I'm saying?
Yes, sir.
So now we know the final temperature is 3 root 2 times initial, right?
Hmm.
Now we can do directly del U1, right?
Yeah, yeah.
CV is 2R
Two
and
hours.
it is 3 root 2 minus 1 after that, right?
Yes, sir.
So you are getting this term as the internal energy change. And now we can sort of write the equation and we'll get Q is equal to this work done plus this internal energy change. You can take 2 RT naught common
Hmm.
and you will get root 2 minus 1 plus 3 root 2 minus 1, right?
Yes, sir. So 4 of it.
1 second. 2 RT naught common. 4 root 2 minus 2, right?
Yes, sir.
Right. So you can now take Q by RT naught is 2 times 4 root 2. 1 second. Feel like I'm making a mistake somewhere. See, this internal energy change is RT naught 6 root 2 minus 2, right?
Right.
And work done is RT naught 2 root 2 minus 2, right?
Hmm.
And both have to be added, right? Yeah,
Yes.
both are positive. So it is 8 root 2 minus 4 actually, right?
Yeah.
Into RT naught. And okay, so 4 can be taken common. It is 2 root 2 minus 1 into 4, right?
Yeah.
Q by RT naught.
Yes, sir.
Okay, that is the answer. 4 times 2 root 2 minus 1. So this is a good question because like you cannot get it immediately. You have to do something, think about it a little bit, right?
Right.
First part of it was actually easy if you noticed adiabatic for the second part.
Right.
That is easy. But once you have that, finding the situation for this gas requires you to do work done by this and delta U1 by this. Work done by that can be calculated indirectly through work done on the second gas.
Yes.
And delta U1, for that we need temperature of this gas. So for that, we need some information from the second gas because second gas gives us the pressure, right?
Right.
Second gas information gave us the pressure that was 3 root 2 or something, right? P naught. No, 2 root 2 P
So,
naught.
yeah.
And once we got 2 root 2 P naught, then we used ideal gas flow to realize that obviously volume has also increased, pressure has also increased, so temperature has also increased.
Yes, sir.
After that, it was simple addition and all. But you have to be patient and you have to not like give up immediately.
Yes, sir.
The question is not difficult, it just requires a little bit of patience.
Mhm.
Okay, next one is this is a diagram. Ideal gas is undergoing a four-step cycle. During this cycle, so the question is during this cycle, heat is absorbed in, and the options are steps 1 and 2, steps 1 and 3, steps 1 and 4, and steps 2 and 4. This is the type of really straightforward questions. There is nothing difficult here, and this is free marks. Do you realize that this is super easy?
Yeah.
So this is JEE Advanced 2021.
1 and 4.
Hmm. One second. Yeah, correct. Okay, next question. This is a thermally insulated cylindrical closed vessel. The height is 8 meter, is kept vertically. It is divided in two equal parts by a diathermic frictionless partition. Diathermic frictionless partition of mass 8.3 kgs. Diathermic means what, you know?
It heat can flow through.
Heat can flow through it freely. The way to say it is a perfect conductor. It will allow whatever heat is required, it will flow, right?
Hmm.
The partition is held initially at a distance of 4 meter from the top. This was the initial distance held initially at 4 meters from the top, as shown in the figure. Each of the two parts has 0.1 mole of ideal gas at 300 Kelvin. The partition is now released and moves without any gas leaking from one part of the vessel to the other. Partition is released and moves without any gas leaks. Okay. When the equilibrium is reached, the distance of the partition from the top will be how much? When equilibrium is reached, the distance of partition from the top, from the top is how much? And they have asked you to take G as 10 and R as 8.3. So straightforward question. You have to understand the process and try to apply it. What kind of process do you think happens here if there is a diathermic wall? Initially, it was 300 Kelvin, 300 Kelvin, right?
Hmm.
0.1 mole, 0.1 mole. As it falls down, the partition falls down a little bit. What kind of a process is it? The overall cylinder was insulated, right?
Right. So overall, I guess overall it will be adiabatic.
Ah, but we don't care about overall. We care about inside the two, no?
Um,
Like we care about what happens to this portion and what happens to this portion.
hmm.
Usually, most of the time when there is a diathermic wall, it will be an isothermal process.
Okay.
Why?
Um,
Because it's a perfect conductor. Any difference in temperature is immediately cancelled by heat transfer.
oh, okay.
Since this allows perfect conduction, as soon as the temperature of one side starts increasing, maybe it wants to increase as it goes down, right?
Right.
But immediately heat is conducted away and the temperature becomes same on both sides.
Okay.
So usually when you see a diathermic situation, it will be an isothermal process. You should keep that in mind.
Yes, sir.
You can do gas law now, right? Let's
Yeah.
say the thing has settled here at a distance of x or something, right?
Hmm.
So initially, what was PV was nRT, right? Initially for this part.
Right.
So initially, you can say what? Pressure into area into force, right? Is
Hmm.
equal to 0.1 into 300 into R, right?
Hmm.
This was the initial situation.
Right.
So 30R was equal to this.
Yeah.
But for the same gas now, it is
Hmm.
P1 new pressure
Yeah.
into area into X, right?
Yes.
Is equal to again 0.1 into 3 because we are saying isothermal.
Yeah.
0.1 into 300 R, so 30 R, right?
Hmm.
And the same equation was true for the other part of the gas also initially, right?
Yes.
But now for that, it will be P2 into area into the distance is now 8 minus X, right?
Yes.
Is equal to 30 R, right?
Yeah.
Do you understand what I'm saying?
Yes.
So basically, we have a situation like this where we have P1 into area into X is equal to P2 into area into 8 minus X is equal to 30 R,
Hmm.
right?
Right.
So for P1, we can take, okay, so we can get the relation between P1 and P2 from here, right?
Right.
Do you understand what I'm saying?
Yes, sir.
You can easily say this is equal to
Equal.
P2 into A into 8 minus X.
Hmm.
And A will get cancelled.
Hmm.
And we are getting P1X is equal to P2 into 8 minus X, right?
Right.
But can we get a different relation between pressure 1 and pressure 2?
There'll be since it's in equilibrium, the pressure
Yeah.
on both sides are equal.
Has. They are not equal.
I mean, plus the
You have to
pressure
get
that is
balanced, right?
yes, sir.
So we can say that pressure 1 plus mg by
And
A
yes, sir.
should be equal to pressure 2, right?
Yes, sir.
So this is an alternative relation and this is another relation, right?
Hmm.
Now you should be able to sort of solve it, right?
Yes, sir.
So try it out. Do you realize I'm getting an equation like this?
Yeah.
Because we had P1 into A into X is equal to P2 into A into 8 minus X is equal to 30R, right?
Hmm.
I'm writing the equation here. I'm saying P1A plus mg is P2A. And then I'm putting P1A is 30R by X.
Yeah, yes.
And P2A is 30R by 8 minus X.
Yes,
And
sir.
by the way, 10R is 83.
83.
So this cancels here. It is a 3 here, right?
Hmm.
So you're getting 8x minus x square is equal to 3 times 2x minus 8. So 6x minus 24. You're getting x square minus 2x minus 24 is 0, right? So the roots of this are minus 6 and plus 4. So 6 and minus 4, right? So
Yes, sir.
6 is the only positive answer.
Mm.
That is the answer, 6 meters.
Mm.
So what was the concept here? The idea was you need to understand what a diathermic situation does.
Mm.
The diathermic wall is allowing perfect heat conduction, so the temperature cannot change for the two vessels, two parts of the gases.
Right.
Once that happens, it's a isothermal expansion and isothermal compression for both the parts, right?
Right.
So we just connect their initial pressures to their final P1 and P2, and we got a condition between P1 and P2 in the final state, right?
Yes, sir.
The other condition that we can say is P1 plus the weight of the partition must be balanced by P2.
Mm.
So these two equations together, if you solve, you will know the X then.
Yes, sir.
Is it clear?
Yeah.
Okay. Next class we'll be doing maths. After that, we'll continue with physics. Okay.
Okay, sir.
So tomorrow we'll do a class for maths then.
Yes.
Okay. That's all for now. I'll see you next time.
Thank you, sir.
Hmm.